Okay, so let's start the lecture. Seems like maybe I lean more towards this side because there's more people now clustering on this side. I'll do my best to lean to the right, as much as I hate to lean to the right. Um, any questions before we start today? Okay, in case you came in late, homework number 1 has been returned to you. As you can see by that big pile there, a lot of people dropped the course. Sorry about the delay in getting back the homeworks to you. I think it'll get a little bit faster, but the way we're doing it now is I like to look through the homeworks. It's a way for me to get to know your work. So I'll go through the homeworks once without grading them, and then I give them to the reader. So there's a little bit of a delay, maybe two weeks. But definitely we'll try to get them back to you before the midterm. I posted solutions to homework number 3 yesterday, in case you're curious. I didn't post solutions to homeworks number 1 and 2, mainly because number 1 was mostly just running SPICE, and looked like most of you guys got it together and did a good job with that. And homework number 2, essentially, we did in class, right? So it's a PMOS version of what we did in class, so it shouldn't be too bad. Okay. Okay, so let's get back into the lecture. Actually, wrong lecture. I think we were talking about high swing circuits. Yeah, I think this is kind of where we left off. Okay, so remember the point of is to design a circuit that has high output impedance, so it's like a cascode current mirror, and also to try to achieve the largest swing possible. And we realize that in a straightforward cascode, you're kind of wasting a threshold voltage. So we want to come up with a circuit that gives us just the right voltage at the gate of the cascode transistor to provide us the maximum possible swing. And an implementation that we looked at last lecture, which is less sensitive to body effects, so it's essentially the same as this circuit, where we generate the right bias voltage by using a quarter-sized device, but then the observation is that these two devices basically don't match. Their threshold voltages don't match because this source voltage is pulled up. Also, to get the maximum matching between the mirror, we insert this transistor, which lowers the drain voltage to 1 overdrive, the same as this device. And then this is a variation on that principle. Instead of generating the reference with one transistor, we generate with a bunch of transistors where the source voltage is slowly pulled up, so we get less error due to body effect. Now, if you had a triple well process, this wouldn't be an issue. You would just tie the body to the source, and you wouldn't have to worry about this. Okay, any questions about this circuit? All right, and let's look at just one more device, and from there we can start moving faster because these are all variations on the same theme. In this version, we're actually going to generate our overdrive voltage with the device in triode region. And the way you do that is you have one device which is diode connected. So for sure this top device, M6, is in saturation. By definition, it's diode connected. And then this device, I'm going to bias it up with the same gate voltage and connect the drain to the source of M6. And the claim is that this device is in triode. Why is that? Anybody have a good explanation for that? Sang, you want to?
So the top device is in saturation, the rest of the channel is across M5, which has to be in cutoff or triode.
Triode, yeah, exactly. That's right. That's good intuition. So the intuition is that this looks like one transistor, right? I've just taken one transistor and broken it up into 2. And so if the top part is the part in saturation, right, the rest has to be in, there's got to be a channel at this point. And if there's a channel at that point, that means this device is in triode region. Okay? And so if you go through the equations, I won't bother here, if I make this a 1/4 device, then you can show that the overdrive voltage of this device is exactly, basically, the voltage you need to bias. Basically, you get one overdrive here. So at this point, you get 2 overdrive plus a threshold voltage. So this is exactly the reference I need to bias up my transistor. So I'll go ahead and connect this to my cascode device. And then over here, I could bias this up through a mirror, just a regular mirror, but I'll use the same trick that we talked about on the previous slide. I'll use another transistor, this bias to the same point, so that this transistor sees 1 overdrive just like this transistor, and I can guarantee that this transistor, I can make this connection as long as the threshold voltage is positive and bigger than the overdrive voltage. And so there you have it. Okay. Questions? Yes, Shiji?
Why the gate of M6 is 2 overdrive plus VT?
Okay, I didn't show that to you. It's you go through the equations and you can show it. In fact, I think here's a design example. And you know, take this example with a grain of salt, because we're assuming here short channel devices, square law behavior. So this is a good starting point for SPICE. And then you can go into SPICE and optimize. But if you work out the equations, you can show that this is true. Yeah. All right. Any other questions? Okay, and then there's a final example here, which is almost the same thing. Same concepts, right? Now these structures start to look familiar to you. You have this structure, which generates an overdrive in triode region, right? You've got this structure, which is just to give us the same voltage here. And the difference is that this particular mirror allows us to have different links on the cascode device. And this is actually something that's very often done, right? You don't necessarily want to size your cascode device the same as the bottom transistor for frequency response reasons, for noise reasons. And so here, this circuit lets us get a shorter channel length on this cascode device. Okay, and then here's another example. Again, I'm not going to go through it in detail. There's lots of these examples. They all are more or less the same. One thing you may notice about this particular example is the device sizes are now getting to be a little bit awkward. Before we had a device that was a 1/4. Now we have a device that's a 1/16. And based on what we've learned in this class, we know we're not going to lay out a 1/16 device by cutting its W by 1/16 or its L. We're actually going to do identical copies, right? We're going to do replicas. And that means that your layout's getting pretty big to implement this high swing bias. Okay? Now you may make the argument that why not just spend a week and design a really good high swing cascode bias circuit and put that in your library, and then whenever you need it, or basically even though the area is quite large, why not just have one of these and then share it all over the chip? Right? That kind of makes sense, that you would have maybe one reference, and everywhere you have a cascode, you just pick off this voltage and use it. Is that a good idea? Pretty good idea, right? Saves area, saves current. What are some of the dangers of doing that?
Layout mismatch.
Yeah, in fact, that's something we'll talk about towards the end of this subtopic. But great, yeah, matching is an issue. You know, when transistors are close together, we know matching is very good. So if I'm using this and then I have another amplifier that's a few hundred microns away, the matching between those transistors is going to go to hell. So we're not going to, you know, you might get into a situation where 3% of the parts fail because the voltage is too low and it drives your cascode into saturation, for instance. Okay. Any other reasons why I might not want to just have one bias generator and use it all over the place? It's kind of a more general question.
Used to be IR drop.
That's right. IR drops is another issue we'll talk about. Takes parasitics, right? You have to route voltages around, and if currents are flowing through, then you have an issue. But what about just routing a voltage, right, with zero current? If I'm just taking this voltage, right, there's no current going into my cascode device, so there's no current. So then the resistance doesn't matter. Any other reasons why you might not want to share? Yes?
It's going to pick up noise.
Yeah, that's the biggest problem. You know, if you have, so let's say I have some bias voltage generated here, and it goes off into a bunch of different amplifiers. Well, the issue then is that if there's any kind of noise on this pickup here, it's going to basically route that noise to every other circuit, right? And these wires, if they become quite large, they actually become good receptors of noise. So they pick up noise, especially if we're not careful and we unintentionally introduce a loop in our layout. So then now magnetic flux gets picked up here and can generate noise. And so basically, even though it's a nice idea to have one master bias voltage and just route wires everywhere, it saves power and area, a lot of times it's actually a safer bet to put things close by, especially if the power penalty is not too large. Okay, Amin, you have a question?
Even if you use different branches for each subcircuit, you use a different branch, so it's a common reference for different branches to copy, so we still get the same problem? Or?
Yeah, actually this is a good time to talk a little bit about this topic. So, in fact, let's maybe skip ahead and talk about, it's not even in this lecture. Okay, so let's talk about voltage. Let's talk about this general idea of basically routing bias voltages. Okay, and there's actually, so one way to look at it is I could have one cell that generates some reference voltages for me, and then in order to generate bias currents for different blocks, I could just have current mirrors. So here somewhere there's a diode connected device, right? And I basically route like this, and in order to route currents to different parts of the circuit. Okay. Now, we've already discussed some issues with this. One is matching. And in fact, this is probably one of the biggest reasons why we don't want to do this. Because these transistors are physically far away, their threshold voltages are going to have a mismatch, and there's going to be a big problem. Now, threshold voltage mismatch, if we come to this summary, sorry to switch gears several times on you here. So matching, let's talk about matching in particular. So matching, there's several issues. There's systematic mismatch, and then there's the random mismatch. Systematic mismatch is things that you can do something about, right? We talked about this when we talked about resistors, capacitors. For instance, just a delta VDS introduces a mismatch in currents. Certainly, if we design our circuits cleverly, we don't introduce any delta VDSs in our current sources, right? So that's easy. Source resistance. This is something that Toda brought up, right? You have IR drops. If you're routing currents, any kind of resistances that you introduce will introduce mismatches. So for instance, if I come to this picture here, let's say just because of the way I've laid things out, I introduce more resistance here. Then certainly that would cause a mismatch in the currents. Fortunately, this resistance doesn't really matter. In fact, this resistance is somewhat beneficial because there's no current going through here. Why is this resistance beneficial? Yeah, noise rejection, right? Because this kind of looks like a distributed RC line. And so if I have any kind of noise, let's say pickup on this gate, it'll get attenuated by the time it gets to the reference, and so it has less chance of infecting other circuitry, right? Okay, so the other, you might call this systematic. If we go back to the slide, you might call this last thing gradient systematic, or you might say it's random, depending on your perspective. If you're a circuit designer and you've got chips back and the threshold voltage is varying all over the place, it kind of looks random to you. But some process engineer will say, if we make a plot of the threshold voltage, there's contours of constant voltage, and that's because of the way I injected my ions and who knows what. So, okay, more or less it's random. And if you actually now look at how that impacts, let's say in particular a current source, the threshold voltage is going to vary, doping variations and so on and so forth. And also there's going to be lithographic variations. So there's going to be, we're designing very small transistors, so when you put down 1 micron, it's going to be 1 micron plus delta. More importantly, the channel length is very small, and it's 0.1 micron or 0.18 micron, and it's going to vary, and that's going to introduce variations. And you might argue that C-ox is going to vary, right? Thickness of the oxide is very thin. That should vary. Mobility should vary, because mobility is also a function of doping. But for simplicity, we're going to lump all the mismatches into this term. And the reason we can do that is because they're all multiplied together, right? You have mu C-ox W over L. So let's just lump it and call this mismatch delta W over L. So it's an effective W over L mismatch that compensates for C-ox and mu. Okay? Now, how many people have done these kinds of calculations where you do mismatch calculations before? Okay, a couple people have seen this before. If you haven't seen it before, at first it looks a little intimidating, but it's actually quite simple. So what we do is we say, let's say I have 2 transistors and they're in a current mirror, and their VGSs are equal, and I want to know how much their currents differ if I change their W over Ls and if I change their VTs, right? And so what I'm interested in calculating is the variation, delta I, normalized to I, right? And let's say I can tolerate a certain amount of variation, 1% or 5%, depending on the application. So the way you do this is you define average quantities and difference quantities. So the average current obviously is 1/2 ID1 plus ID2. The average W over L is just that. The difference in WLs is that. Again, you have a difference in threshold voltages and an average threshold voltage. And if you go in and you plug in, so if you substitute, you invert these equations, you write VT1 as a function of VT plus delta VT, right? VT2 as a function of VT minus delta VT, for instance. You plug all these in, take the difference, you do some algebra, you get this nice clean expression. Okay, so let me write that expression a little bit larger here. So when you derive this, the key thing that you need to do is you neglect higher order terms, meaning when you're doing this calculation, any term like delta squared, you just assume it's approximately 0. So you want to know the first order variation in the output current due to first order changes in WLs and VTs. Okay? So this expression is really nice. In particular, it tells us that we have at least one knob to turn in terms of bias voltages in order to minimize mismatches, and that's VGST, which is really what we've been calling V star in this class, right? So if I want to design current sources, current mirrors with good matching, I should bias them up with very large V stars. Okay? How does that impact noise? It's good for noise too, right? So large V star is good for matching, and it's good for noise. But, of course, it's bad for swing. Okay? So, in fact, this gives us a very nice recipe for routing currents and voltages, because if I come back here, if these transistors are really far away from each other, then I'm better off. I can still do this as long as I use a large V star to reject the threshold voltage variations. Okay? How do I solve the problem with swing, right? Anybody have a suggestion? Let's say I want to use this current source as a load for a PMOS amplifier, right? Because it has a large V star, it's great, it has low noise, but it's going to have, and it has good matching, but it's going to have a really poor swing. Yes, Shiji.
Can use a lower VD set in the output stage. Try to use a DC bias level shifting.
Well, okay, I think I know what you're saying, but you probably don't want to make that compromise, right? You probably... So, one thing you can do is you can kind of make this... Anybody have another suggestion? Okay. Let's say you're willing to dissipate a little more power. I'll give you a hint.
You can use the current to and mirror it to another current source.
Yeah, there's nothing sacred about this mirror. I can make another mirror, right? So I have my, let's say, my large V star device, and then I mirror it again. So this is a small V star device. And so here I have a large swing. Okay.
So another question related to this: don't people usually use reference currents?
Yeah, we'll talk about that. Yeah, good point. Yeah. Before.
Does that small V-star device will kind of introduce more noise?
Yeah, it's a penalty you pay, right? Yeah. So you've made some kind of noise swing dynamic range trade-off already. Before I go to your point about currents, one last point. Can anyone think of a way of improving this circuit? The circuit is very... It can pick up a lot of noise, right? Why is that? Let me give you a hint. Right now, it's very susceptible to picking up magnetic fields, right? Is there a way to improve that susceptibility?
So you may have ground loops.
Very good, ground loops, right? So I think one of the most dangerous symbols electrical engineers invented was the ground symbol, because it's this nebulous concept. Oh yeah, it's ground. But in reality, when you lay out a chip, you realize, wait a minute, how does ground get to this point? Certainly I'm not going to rely on the substrate to be my ground, right? The substrate is too resistive and too noisy. So usually there's some kind of ground bus in your chip. So you might have this big bus going around, that's your ground, and so then here this would be a local connection to ground, and you would say, okay, great, this is a low resistance path, I've strapped this with a lot of metal, and great, that's low resistance. But as Toda pointed out, because there's current flowing on this path, any kind of resistance here introduces a mismatch. So you do a really good job, you do a good layout, and there's very little resistance. But now you've introduced a huge loop, right? And so if there's any kind of magnetic fields, let's say coming in perpendicular, so these are B fields, then that introduces a voltage around this loop, which causes basically your bias current to vary with the frequency of the B field variation. Okay? Where does this magnetic field typically come from? Can you use the mic?
So you have a change in current. Maxwell's law says you have a beefing.
Yeah, it's all over the place. In particular, one big source of it are bond wires. So typically bond wires are going off chip. They carry large currents. And if they're carrying high frequency signals, there's a large DIDT. And so this generates magnetic fields that can couple into your circuit. So it's really bad if the output stage is coupling back into its own bias stage, right? It's a feedback path. It might cause you to oscillate. It might produce some mysterious spur on your spectrum analyzer that you just can't trace, right? So what's the solution to this problem? Let's get someone else. Okay, anybody can think of a way to still route this voltage but eliminate this large pickup? Okay, Lee?
Put a capacitor ground?
Yeah, it's a good idea, right? If I put a capacitor from here to here, this will work, but unfortunately this only works at high frequency, right? So at really high frequency is beautiful. It does a great job. This is called the decoupling cap, because it decouples your bias circuit from all this stuff. Okay?
Could you reduce the loop area by routing the lines together?
Yeah, the solution is very simple. If you're just willing to take two wires, you're done, right? Now the loop is very small, and so you're less susceptible to pickup. And in fact, you can put these wires very close together, right? So there could be almost very tiny area. You can reduce the area by several orders of magnitude. Okay? Questions or comments? All right, so let's go back to Michael's point about current routing. So another option you could have is you can route currents. In other words, instead of putting the mirror device far away, put it close by, where the threshold matching is good, and then you route this current to your circuitry. Okay. Any comments about this approach? Benefits, or first of all, one benefit is that you're now not sensitive to matching because you're taking advantage of the fact that the transistors are close by. Okay. What are some disadvantages of this approach?
Would the IR drop over the wire reduce your swing at the load circuit?
Yeah, that's a potential issue. Yeah, so you have basically you have resistance here, and that IR drop could start to eat away at your budget. But usually, you know, the current levels we're talking about, milliamps or hundreds of microamps, probably okay. Any other issues with this approach? Well, one thing is I can't share these bias currents, right? With a bias voltage, at least if I wanted to, I could have shared this voltage. So here I could have shared this voltage with a bunch of other blocks and basically just had one wire going out there. Of course, that makes this more susceptible to interference, because if one block has noise, it couples to the other blocks. Here, though, I have to route currents to every circuit separately. It's not a voltage that I'm routing, it's a current I'm routing. And so this may involve a lot more wires, right? So more layout. Let's say more area. What's another disadvantage of this approach? Well, think about it this way. Let's say this is a diff pair. Oops. Okay. Noise from where?
Your current source, your current's not clean, so that gets modulated to the output through the...
Okay, that's a potential problem. I was looking for something else.
Do you lose current through the capacitance in the wires?
It's a DC current, right? So it shouldn't really be a problem. But you're onto something. Why is it that I don't like capacitance on this line? Yes, Debo.
Coupling between.
Yeah, sure. That's an issue. But
I mean, you'll get displacement currents, right, that are AC, that'll put in noise.
yeah, you're absolutely right. So if you have, I guess both you and Debo were talking about substrate noise that could get into your bias. Yeah, that's a potential issue, definitely.
Does that look like a transmission line so that will, I don't know, high frequency stuff?
Yeah, as we talked about, the fact that it's a transmission line kind of helps you, right? It kind of attenuates. It's a high loss transmission line, so attenuates signals nicely. All right. So if I'm designing a diff pair, why do I use a current source here, right? I could just ground this point. It's a virtual ground. Why use a current source? All right. Anybody? Why is it I don't like having extra capacitance on this node?
Well, common mode rejection.
Yeah. At high frequency, the common mode rejection of the circuit is a function of how much capacitance I have, right, at this point. And if I have this long wire, then there's going to be lots of capacitance. It's that simple. So
That's kind of high frequency stuff, right?
not necessarily very high, a few megahertz, right? I mean, depends. Now, looking at all these issues, you see there is no magic bullet, right? There's voltage routing, it has some problems. There's current routing, it has some problems. Usually, a real chip uses a combination of techniques. And one approach, which is popular, is you current route globally and then locally voltage route. So this would be voltage routing, and this would be current routing. And you do the current routing so that you're not sensitive to threshold voltage variations, and then locally you can do voltage routing. Okay? So global, current, local voltage. All right, so that's a little bit of a detour, but I think it's an important detour. So let's get back to the lecture. Okay, so we talked about methods of designing a high impedance current source. One is a cascode. How do I get more impedance than a cascode, right? So I'll just draw a standard cascode, not a high swing version. Let's say this is not quite enough output impedance. Let's say I want even higher output impedance. What can I do? Don't look at the slide. Besides what's on the slide, what else could you do? Stack more, yeah, why not? In MOS devices, you can just keep stacking. It doesn't hurt. There's no base current like bipolar, and so the impedance just keeps going up. In fact, with 3 stacks like this and with a long channel device, the impedance you get here is so high it's probably larger than you can possibly measure. It's probably a few gigaohms, and just leakage currents alone are lower impedance than that, or just so basically this technique is great. You can get to very, very high impedances, but what's the price? There's no swing left, right? So at the end of if you're on a 1 volt supply, forget it. This is not going to work. And so the other technique that's becoming popular now is gain boosting. Okay? So the idea of gain boosting is that we're going to use feedback in order to boost the impedance. And the way that I like to see how gain boosting works is to go back and look to see how a cascode actually attains high impedance. And so in fact, a cascode already is using feedback, right? So in a cascode device, if I put a test source here that sends in a test current, that test current flowing across here produces a voltage Ix times Ro, right? And that produces negative feedback on this transistor, right? So this actually excites the transistor. Let's just do a quick calculation for how this works. So this current, let's call this GM2 VGS2 RO2 RO1. So this current Ix, let's say at low frequency, let's ignore the contribution here, mostly flows here, so that VGS is minus Ix RO1. And so here, in order to calculate Ix, I calculate the voltage drop across here, right? Plus the voltage drop across here. The current through here is Ix minus the GM generator, right? And so then I could write this as Ix RO1 plus RO2 minus GM 2 RO2 VGS2. But VGS2 we just found is minus Ix RO1, so Vx over Ix, which is the output impedance, is RO1 RO2 plus GM2 RO1 RO2. Okay, this is a trivial calculation that you learned in 140. But the lesson to be learned is that it was the voltage at this node, which the larger I can make this voltage here, the more action I get out of this transistor. So how can I even boost the voltage more? Well, put an amplifier there. So if I have an amplifier at this point, and I do the same experiment, I'm not going to redo the math, I think it's obvious now that instead of, so this last term here, the contribution was minus GM2 RO2 VGS2, well, I'm going to make VGS2 G times Ix RO1 minus, right? So then the Rx goes up. Let's just drop the other terms, they're small. GM2 RO1 RO2 times G. So I can boost my impedance by a factor of G, where that's the gain of this amplifier. Okay. What are the issues? Right? This seems like a great idea. In particular, I don't need any headroom, extra headroom to do this. I can just have a regular cascode, right? This could be a resistor, or better yet, it could be, in fact, a transistor. So I can, again, operate this right around an overdrive voltage, and with the same headroom as a cascode, I can get a really high impedance, right? I can make lots of gain here, right? So, what are the issues?
Complexity.
I'm sorry?
Complexity.
Complexity, okay. We've got lots of transistors to throw around, right? Complexity doesn't slow down the digital designers, right? So why is it the complexity is scary? Okay.
I don't understand why your overdrive doesn't go up. Because if your VGS goes up, doesn't your VDS have to go up too?
Okay, so small signal versus large signal, right? So this amplifier is only acting on the small signal, right? Okay. So what is it about complexity, Shiji, that is particularly concerning? You're right, right? It's a more complicated circuit, but what is it about it? It's not just transistors, right?
Papa introduced more poles.
Yeah, exactly. Stability. Stability is an issue. In fact, if you haven't done the analysis and you look at this, your conclusion might be that, wait a minute, why am I doing this current source? I'm not doing it just because I want to generate a tera ohm of resistance. I'm doing it for gain, right? I want to design an amplifier with lots of gain. And doesn't that imply that this loop has to be faster than my amplifier loop for this idea to work? Right? Doesn't that seem to be the case? So if my amplifier has a bandwidth of 10 megahertz, it seems like this thing ought to have a bandwidth of 100 megahertz, so it doesn't interfere. Right? In fact, it's not so obvious. And one of the surprising results is that, in fact, no, you want to make this loop slower than your amplifier for stability reasons, not faster. So, in fact, stability is a concern. We have to look at it carefully, but it's not a showstopper. It doesn't, otherwise it wouldn't be talking about this in this class. Compared to a regular cascode, though, what other potential issues do we have to watch out for? I think I see you saying it. Noise, right? Yeah, noise, right? Potentially this thing can have higher noise because this amplifier obviously is noisy. It injects noise onto the gate of this device, which makes its way to the output. Without doing any math, are you concerned about that noise at low frequencies? Debo, you're shaking your head. Why not?
We rejected it's a cascode.
Yeah, remember last lecture we looked at any noise on this device. Oh, here's a very easy way to look at it. If I have an input referred noise voltage, the transfer function of the output is basically the gain of this device, which is heavily degenerated, right? And so very little noise is going to make it to the output. High frequencies, though, the story is different. So high frequency noise is going to be a big issue, right? All right, so here is a simple circuit that implements this idea. Let's switch the slide. And basically you have your regular device, M5. You have a regular cascode device with M3 and M4. And to make the frequency response more obvious, we've inserted a capacitor here on purpose, a 10 picofarad capacitor. And then you have this gain boosting. So you take this voltage and you gain it up by 10, and then you low-pass filter it and go into this device. Now this low-pass filter is very low frequency, it's 10 hertz. So we're actually purposely introducing a very slow amplifier here. Okay, that's a good thing actually. If I can show you that this idea works with an amplifier with only a 10 hertz bandwidth, you should celebrate, right? Why? That means you can basically run this very low currents, right? Currents are not an issue, so you can do this with very little power penalty. Okay? All right, so schematic makes sense to everybody? Incidentally, there's another way to interpret what's going on here, and the other interpretation is that this op-amp is operating with negative feedback, right? Because this M2 has just unity gain through it. So what it's doing is it's forcing this node to have the same voltage as this node, right? And this node is a constant voltage. So this op-amp, it's doing its best, right? It's putting its loop gain into this action to keep this voltage constant, which means that the drain of M1 doesn't vary, which means that its current doesn't vary. So this is why, this is another perspective on what's going on, and you can see that, in effect, a regular cascode is doing the same thing. With a regular cascode, this voltage here is being held constant because the VGS of this device is relatively insensitive to variations of current, and this gate voltage is constant. So here we're doing one better. We're introducing even more gain into this loop to hold this voltage constant. Okay? Questions? Comments?
Yeah, I noticed that there's two is that low pass filters?
Yeah, so there's two more filters here.
Yeah,
and
is that practically used in the industry or just
this is actually not practical. This is just so that we can isolate the noise of these transistors and neglect the noise, the bias, because we just want to see, yeah. But in reality, of course, it's pretty hard to build a filter with 1 Hertz corner frequency, yeah. Okay, so here is actually a plot of the various output impedances. So this blue line, if it shows up on your screen, the bottom curve is your regular device, okay? And this pink curve is your cascode. So you can see the cascode has quite a boost on the log scale. Notice we're going from 100K to 100M. And the price we pay, of course, is that the bandwidth is not quite as good as the regular device, because we have basically some extra capacitance on that cascode node. And then finally, the boosted amplifier is this top curve. You can see here the gain is 10, so we expect the boosting to be a factor of 10, and that looks about right. So here's a gain of 10, and then right around 10 Hertz, you can see that the boost goes away, right? So you only get the boosting within the bandwidth of the amplifier. Once you go above 10 Hertz, there's no gain, so you would expect that the impedance should actually approach the impedance of the cascode device, right? And in fact, you see that it's coming very close to the impedance of the cascode, and eventually it just looks just like the impedance of the cascode, right? Has no effect. Okay. There's something tricky in this curve that I want to point out to you, and we're not going to analyze it in detail today. We'll come back to it when we talk about stability in more detail. But there's actually what we call a doublet, a pole zero pair, that's hidden in these curves. So the idea is, maybe I should draw this. I think it's easier to see if we draw. The idea is if I use this gain boosting in an amplifier, then probably this is going to be some high impedance node at the output of my amplifier, right? So there's going to be some CL here. So in fact, if I look at the effect of CL, right, if I plot the impedance of CL on this graph here, ZL is just dropping, right? It goes to infinity at low frequencies, and then it just drops monotonically with frequency. Now the boosted response, well, let's redraw this. So this is our regular, let me draw it somewhat accurately here. This is my regular device. This is my cascode device. And then this is my, let's say, my gain boosted device. Okay? So this is actually the impedance that you see out here, real part at low frequency, and it goes out until we hit the basically frequency, 3 dB frequency of this loop, then it drops, then it looks like a regular cascode, then we hit this pole frequency, and it drops, and finally it just looks like a single transistor, because really high frequencies, even the cascode isn't really helping out anymore. Its gain has gone away. But the idea is that the overall impedance looking out here is a parallel combination of CL and this guy. So the parallel combination, of course, is dominated by the smaller impedance. So at really high frequency, it's really this curve that dominates, right? This curve, these curves almost have a negligible effect, right? So if I were to plot the impedance as a function of frequency, at low frequencies, this curve dominates, and then basically I more or less follow this curve. I'm slightly below this curve, right? Because it's a parallel combination. So the parallel is smaller. And you can see that as I cross this frequency here, for all practical purposes, if I plot this in SPICE, I won't see any change. But if you actually think about what's going on, all of a sudden, this starts dropping, right? So there should be a small shift, right? A tiny little shift, because now this impedance is dropping too. Same thing over here. As I come here, all of a sudden this impedance is holding constant. So there's a small shift. And these small shifts are actually imperceptible, right? If you plot them in SPICE, unless you zoom in really close, you won't see them. But they're there. And what these shifts represent are pole zero pairs, almost right on top of each other. So they're almost canceling each other out. And these are called doublets. And if you don't take care of them, they actually can be bad. Your settling time could actually end up being dominated by these doublets. So there's something to consider when we look at frequency response of this amplifier. Okay? Questions? Yes?
If the zero comes before the pole, that would be better for us. That would be a positive point. It wouldn't be.
That's right, because it self-compensates. Yeah, we'll go into details of this later on. Yeah, I want to point it out to you guys for now. There's actually a really good paper that talks about this compensation scheme in more detail. It's by Klaus Bolt, and even though this idea is actually quite old, probably goes back to the 40s or 50s, this gain boosting, it didn't really become practical until this paper was published in the 90s. Okay. Here's a noise analysis of the three circuits. So again, noise analysis of the regular mirror, cascode mirror, and then this gain boosted. And what happened to the gain boosting? So instead of using an amplifier, I'm using an explicit transistor, right? The simplest gain booster is just a single transistor, right? Takes the voltage here, boosts it up, right? It has gain because of this current source. And so this is the world's simplest gain booster, which in fact turns out to be a shunt feedback pair. The reason that we use this transistor is we want to see how much noise this transistor introduces into the overall circuit. In reality, you're probably going to use something more sophisticated than one transistor as a gain booster, just to get more gain. So whatever noise is introduced will be even higher than what we're showing here today. Okay. Okay. So here it is. This is the noise result. So this is the noise density, and you can see that they're all right on top of each other at low frequencies. You have your flicker noise, then you have your thermal noise, and then at high frequency they start dropping off. Except you see the boosted amplifier has a little bit more noise. Okay. Now I say a little bit because I'm looking at this curve. Does that matter? Well, one way to see what the effect of this noise is, remember last lecture, a couple lectures back, we noted that log curves are very deceiving, right? So if you look at this curve, you say, ah, it's a blimp. You wouldn't even notice it, right? But then you look at the axis and you say, oh, this is, remember when you integrate, it's delta y times delta x. Delta x here is huge, right? This little blimp is occurring over tens of gigahertz of bandwidth, right? So it will, it will have an effect. If this blimp had occurred over here in the flicker noise region, it would be totally negligible because delta x would be 0.1 hertz, right? Or 1 hertz. So in fact, if you integrate the noise, boom, you see it. You see that the boosted amplifier, even though it just has one extra transistor, has higher noise. And if you're using this in an application where you're actually picking up noise from all frequencies, like in a sampling system, this noise will hurt you. Okay? The penalty is not so bad. For this simple device, you're going from 35 microvolts RMS to about 40 microvolts RMS. But clearly, if you use more amplifying stages, you'd get even a higher penalty. Okay.
Typical frequency, because I can see clearly that.
So you can see that this is starting to kick up around a gigahertz. Yeah. And this is right around the frequency of where the pole is occurring in that cascode node. The impedance of that node is starting to drop. Okay, here's kind of a zoom in on the noise. You can see where the different noise terms are being contributed. So the cascode noise, you can see, is heavily attenuated. Oops. Cascode noise is heavily attenuated until you get to high frequency. Same thing with the booster noise. It's also attenuated until you get to higher frequencies. Yeah, this is exactly the intuition that we had about the impedance of the cascode node. All right, so this is kind of funny. If an idea works, why not just do it again, right? So it's almost hilarious. You take a gain boosted amplifier, and then to design a higher gain amplifier, you gain boost inside that amplifier, right? So it's nested gain boosting. And in fact, a student from Berkeley presented this at ISSCC a couple years ago, Yoon Chu. And this is a paper reference if you're interested. It's in the Journal of Solid State. This is what we call the red rag. December issue is actually the ISSCC issue. So this was presented at ISSCC and then as a journal publication. And this was a part of a pipeline AD converter which had a very high dynamic range. In this particular case, he ends up getting a gain of something like 130 dB out of his amplifier. And this is, I believe, a 0.18 process, or maybe 0.13. But no, it looks like it's 0.18 by the supply voltage. So that's pretty good. That was actually probably the highest gain reported in that technology. In fact, the gain is so high that you probably can't measure it, right? Just any kind of, if you blow on the thing, the gain changes, yeah? When the gain is so high, right, any kind of parasitic feedback lowers the gain. So, there's parasitic feedback just through the air, right? Just the fields coupling from the output back to the input. Even though it's very small, it has loop gain because your forward loop has so much gain. Thermal feedback is another thing. One transistor gets hotter, threshold voltage of a transistor nearby changes. That's a parasitic feedback path. They're sitting on the same substrate. Okay.
Yeah. What's the power of this circuit?
Oh, I don't remember. Yeah.
Is that huge?
No, it's very reasonable. Yeah, it's very reasonable. Because the reason it's reasonable is that you don't need much current in the gain booster. Yeah, and in fact, the analysis of this frequency response is quite complicated because you have doublets within doublets, and so you have to take that into account. All right, we talked about matching. One last point about matching. So, in fact, we showed you that this equation here describes the matching for current mirror, and in practice, of course, these mismatches are not fixed quantities. They're not systematic. They're random, right? So in reality, what we're interested in is the variance of the mismatch, right? So it's kind of like a measure of the average mismatch that we get, and so we sum up variances, right? They're random variables, so we don't sum up the standard deviations, we sum up the variances. So again, this is just this equation with each term squared. Now the assumption here is that the statistics of these, okay, what justifies this assumption? It's partly that these processes are independent, right? They're uncorrelated. Just like with noise, if they're correlated, I have complications. I'm going to assume they're uncorrelated. Even if they are correlated a little bit, who cares, right? So if they're uncorrelated, I can just sum up variances like that. And so here's a kind of a numerical example which gives you a little bit of insight. Let's say that the fab tells you that if you put two transistors nearby, the variance of the threshold voltage is about 3 millivolts. Okay? And so then to combat that, that tells you, if you want to have, let's say that you also know that your W over L variance is also 1%. So what you'd like to do is bias your device with enough overdrive voltage so that the overall mismatch, let's say, is within some spec. In this case, 1.4%. So that means that if you do the math, you have to put 300 millivolts on your device to get 1%, so that 1% plus 1%, right, is square root of 1%, or 1.4%. Square root of 2 times 1%. So we get 1.4% overall mismatch. Okay. Now, what does that mean? Well, this is directly impacts the yield that your circuit is going to get. Let's say that you're designing an A to D converter, and in your A to D, if the mismatch gets too large, your A to D basically doesn't meet specs. Okay, and we'll talk about what that means later, or a lot more in 247. But from perspective of this class, you need to design mirrors that are pretty precise. Okay, let's say that you need 2.8% matching to use this example here. In other words, as long as the mirror currents match within 2.8%, then the part satisfies the specifications. Okay, and you've designed a current mirror that has a match of 1.4%. Okay, that's good, right? What's the yield going to be? Well, if you assume that you have Gaussian statistics, right, kind of the normal bell curve, then it's very simple. You just look it up in a table, or you calculate with your calculator that the area, so within one standard deviation, how many parts are within one standard deviation? Anybody remember? 68, I think it is, something like that. Yeah, so 68%. What if you go within two? I'm cheating. I have a table here. So, what if you go within 2 standard deviations? Yeah, it's 95%. And so on. And so, in our particular example, we have a spec, right? As long as we fall within here, we will meet spec. And our standard deviation is basically 1.4%, and we can tolerate 2.8%. That means that our yield is going to be 95%. Okay, that's pretty good. Typically, if you want to be very, very conservative, you'll do something like a plus minus 3 sigma, and that means that your yield is 99.7%. So, you know, customers got to test a lot of parts before they find one that doesn't meet spec. So, you know, usually when you buy something and someone tells you, well, the offset voltage is 10 millivolts, okay, what does that mean? You can call them up and ask them, but probably means 6 sigma or plus minus 3 sigma. So really, you've got to try really hard to find an op-amp that has more than 10 millivolts of offset voltage, okay? Just a philosophical question. Why is it that everybody in the world just assumes everything is Gaussian? I can give you one answer, right? It's simple. It's very simple. But what's a better answer? Mathematics is simple.
The theory of if there's so many, I don't know the name. Yeah.
Yeah, central limit theorem. Okay, who's heard of the central limit theorem? Okay, about half the class. Good. If you haven't, go look it up. So the central limit theorem is quite amazing. It tells you that if you take a sum of identical independent random variables, doesn't matter what their statistics look like. They can be uniform random variables, right? They can have some crazy statistics. It doesn't matter. If you sum them up, as long as they're independent and they all have the same distribution, at the end of the day you get a normal curve, a bell curve, Gaussian statistics. And it's actually quite amazing. So when someone told me this in college, I didn't believe it. It was just amazing. So I went on my computer and I ran a bunch of simulations, and boy, it works. In fact, you don't even need to add that many independent variables to get a bell curve. That's why anytime you guys take a test, it comes out to be a bell curve, right? You guys are independent and you're identical, right? You all have the same kind of brains, and the test score is the sum well, you can think of it this way. The test is the sum of a bunch of questions, right? And each question, within each question, you get some distribution, and you're summing up. So one question might be really easy. You all get it, you know, if you were in class on this day and you heard me say this word, you all get it. So that one has a really easy statistic, right? The other one might be more complicated, but you sum them all up, you get something that looks pretty much like a bell curve. Kind of, right? But it's a very universal thing that pops up all over the place, and there's a good reason it pops up. It's because it is fundamental statistics, right? I mean, this is mathematics. Interesting thing, though, if you go out and buy resistors, let's say you go out and buy 1% resistors, and you plot the statistics, it won't come out Gaussian. Anybody have a good explanation for that? Okay, Christian?
I think when they manufacture them, they just look at them. Whatever is within 1%, they sell them as 1%. Whatever is within 10%, they sell them as 10%. So you're not going to get a random distribution.
That's right. So what the manufacturer does is they hire some cheap labor, and the cheap labor sits there and measures each resistor. If it's within 1%, they throw it in trash can 1. If it's not, they throw it in trash can 2. Trash can 1 becomes precision, expensive resistors. Trash can 2 becomes, you know, cheap resistors that they sell. So basically, they're taking, let's say, all the parts that fall in here, and they're selling them to you, and then all the parts that don't, they sell them to you separately. So the distribution are these weird cutoff Gaussians, if you like. Okay? Questions or comments? All right, so I hesitate to say let's go to the next lecture because the lectures are totally out of sync with the actual lectures. So maybe I'll go in and rename all the lectures topics instead of lectures. And in previous courses I've taught, I've always waited until the end of the course, chopped off the lecture to the point we actually got to, and then posted it. But the feedback I've gotten from you guys and from some of the reviews is that you really like to have the lecture before class. And so I'm doing my best to post them. So if they're not posted, check the night before. They will be posted. So that you can bring them to class and make notes on them. But that means that just naturally we're going to fall out of sync between actual lecture and topics. Okay? All right, so now we're going to talk about references. And what is a reference? Well, anytime someone draws a current source in a schematic, right, by default it's a reference. So when I had a mirror, I always start out with some current source here. Okay, let's skip to the, let's switch to paper. Thank you. So I have some reference current and I mirror it, right? So the question is, where does this reference come from? Okay. Well, if you're a graduate student, sometimes this reference is just a resistor, right? If you're in the lab and you're testing a part, didn't have time to design a fancy circuit, they just have a resistor. And you have the luxury that you can go outside and you can vary this voltage just to get the right current, and then you're happy and you test your part. But of course, if you're designing something that where there's going to be a million copies of it, you're not going to have someone tweaking a resistor a million times. So we need to design a reference. In particular, we want this reference to be hopefully independent of supply. In other words, the supply voltage varies for many reasons, right? The battery voltage changes, right? One day it's 3 volts, the next day it's 2.7 volts. Talk on the phone for 30 minutes, the voltage drops on your battery. So there's natural variations, and so if the bias currents change significantly with supply, it's going to be a bad idea, right? But also there's noise on this. There's basically the supply is connected to all your circuit, including the digital, at some point. So there's going to be some natural ripple on that supply due to noise pickup. And if our bias circuits aren't sensitive to that, it's really a bad thing, right? So how are we going to design references that are independent of supply? Perhaps we want them to be independent of temperature, right? You don't want your phone to sound worse on a cold day than on a hot day, like this morning. But sometimes you actually want to purposely introduce temperature variation. So for instance, if the GM of this transistor, right, is proportional to I, then as it gets hotter, I may want to increase the current so that I can, basically, at the end of the day, maybe I want a constant GM. And since GM varies with temperature, I might use my current variation to actually track and hold the GM constant. So maybe you want independent of temperature, or maybe you want a certain temperature profile. For instance, you want it to be proportional to temperature or inversely proportional to temperature. Okay. Some other issues. Sometimes we need very basically small currents. For instance, I may be biasing up a circuit that's running in sub-threshold and I need 10 nanoamps of current. How do I get 10 nanoamps? Well, that's easy. Just use a big resistor, right? Well, sure, but that resistor is going to vary plus minus 10%, right? That's one issue. Another issue is that your big resistors are a bad idea on chip. They take up a lot of area. So there's got to be a better way of generating very small currents. Okay. What else? Yeah, so I guess that's it for here. So here's, go through the slide real quick. So this is kind of a summary of different references, and everybody here took 140, right? Who didn't take 140? Okay, one person, but I'm sure you know this stuff. So you've seen this material before, so we can go a lot faster. In particular, we're going to focus on 3 voltage references: PTAT, proportional to absolute temperature; band gap reference, we're going to go through very quickly; and other kinds of references like VBE references and threshold references. One thing that's interesting about references is that all the good references out there are voltage references. Okay? So what if you need a current, right? In fact, a lot of times we need a good current reference. How do you get a good current reference? In fact, if you can come up with a good current reference, you can pretty much write your own PhD. You're done. There is no good current reference that we know of. So if you need a current, you generate a precise voltage, then you drop it across a resistor, and you get a current. Well, you don't have precise resistors, right? So if you need that current to be very accurate, you're forced to use an off-chip resistor. Note that it's an absolute, the current is proportional to the absolute value of the resistance. So using all the tricks that we use in integrated circuits, like ratios of resistors, it just doesn't help. What you have to do if you need a precise current is to have a precision resistor off-chip, 0.1%, right? You go and the person who threw that resistor in that bucket, you take it, and it's a precise resistor and you get a precise current. So that's one thing to keep in mind, because if you can come up with something, boy, that would be great. What are some of the specifications for references? Well, accuracy is important. How much does the reference vary as the supply voltage varies, for instance? Temperature coefficient is important. How much does it vary as the temperature varies? Very important. Power supply rejection. How much does it vary with the power supply? And here we really need to focus on higher frequencies. A lot of references are great at low frequencies, but at high frequencies they are terrible. Other considerations: do you need trimming? So one option, instead of having an external resistor, is you could have an on-chip resistor that you trim. So when you manufacture something, there's some trimming cycle where you measure an on-chip resistor and you have a fuse, or you have some switches, or maybe even a physical laser that comes in and changes the width of that resistor. These are trimming techniques to get precision resistors. Okay. And then other concerns are like, how much supply voltage do you need? How much power does it dissipate? Okay. So this is the poor man's reference that, or maybe it should be called the student's reference. All my students seem to do this when they design circuits. I did it too. Okay, well here's some really simple references that to first order are independent of supply, right? And the idea is very simple. Instead of using the supply as a reference, I'm going to use VGS as a reference, or better yet, even a VBE as a reference, because VBE is almost constant, right? If the current increases by 10x, how much does VBE change? 60 millivolts, right? Log of 10 is 60. So 60 millivolts. That's great. That means that the current can vary all over the map, and this thing, the voltage, is going to be roughly VBE on, right? Plus or minus a few millivolts. And so if I drop that VBE across this resistor, it's going to be a very precise current, right? Okay, here's another circuit that's essentially the same thing. What we're doing is, again, we're using just now one VBE across here and using shunt feedback to produce a low impedance at this point. But again, the idea is very similar. And one thing I didn't mention is that, okay, no, I'll skip that. I'll come here. Here's another reference. Again, you guys have mostly seen these things, so I'm going to go fast. This one is called the peaking current source because if you look at the current, it has a peak value in it, as you very are. But what's useful about this circuit is it allows us to realize very low current. So I can generate nanoamp levels of current by using reasonable sized resistors. A few hundred ohms, I can generate nanoamps. So this is one useful product of this current source. Another nice thing about this current source is that I can make it first order independent of supply voltage. And to first order. The idea is that if I look at this voltage at the output, voltage of the output, let's say I take the voltage here, is VGS minus IR2. So if I look at the derivative of the voltage with respect to current, as this current varies, that's dVGS dI minus R2, right? And what's dVGS dI? Well, it's GM, right? 1 over GM. So to first order, if R2 is equal to 1 over GM, then this voltage out here varies very little, even though this current changes. So this is a very cheap reference that has almost constant current as a function of supply. Okay, here's another very popular reference, the Weidler reference, and again the idea is very similar. I'm going to use these VBE loops here across this resistor to generate the current. So the current is, to first order, the difference between these two VBEs dropped across this resistor, right? And the difference between two VBEs can be very small, right? So I have a very small voltage dropped across the resistor. I can get very small currents. So this is one application of the Weidler reference. If you write the equations, you have that VBE1 is equal to VBE2 plus basically this voltage drop. And if you substitute, if you assume the exponential characteristics for the transistors, you have VT log of current over saturation. And you end up with basically a transcendental equation. So you actually can't solve this equation closed form because you have log of I plus I. And you just can't invert that. But of course you could just plot it, right? Here's IC2 on this graph, and this is IREF. And you can see that, for one, you can program your IREF to get a given value of current. And for two, because this is the log function, it doesn't vary much, right? So you almost get this supply independence automatically, because as IREF changes, right, by decades, then VBE just changes linearly, and so that the current changes very little. And so this is nice. This is a nice property of the Weidler reference. Next lecture, though, we're going to take the Weidler reference and turn it into a PTAT, and then a band gap, and then a bootstrap band gap, and so on and so forth. So, next lecture.